Our universe is a carefully woven tapestry of galaxies, not a random splash of stars. This grand design is known as the cosmic web, the largest structure in existence, and its hidden architecture dictates where every single galaxy can form and thrive. By the end of our journey, you will understand the invisible framework that gives our universe its shape. We will explore the dark matter skeleton that holds everything together and confront the startling possibility that we might be living in one of the cosmos's vast, empty deserts. How does it feel to know your home galaxy is just one thread in this unimaginably large cosmic tapestry? This cosmic tapestry is woven from three distinct threads. Vast, empty voids stretch for hundreds of millions of light years, forming the universe's great deserts. Connecting them are dense filaments, the cosmic superhighways where galaxies are strung like glittering beads. And where these threads knot together, they create immense clusters, cities of thousands of galaxies bound by gravity. This entire structure is not a frozen monument. It is a living, breathing entity, constantly evolving from a set of ancient instructions written into the fabric of space itself. Those instructions were the faint, quantum ripples from the Big Bang, tiny imperfections in the newborn cosmos. Over billions of years, gravity acted as a master sculptor, amplifying those tiny ripples. It pulled matter toward the slightly denser regions, carving out the voids and building up the filaments and clusters we see today. Every galaxy's location, including our own Milky Way, was ultimately determined by this primordial blueprint. By reading this grand architecture, cosmologists are essentially reading the autobiography of the universe, tracing the story from its first whisper to its current, magnificent form. To truly understand this story, we must start with the invisible component that holds it all together, the hidden skeleton of the cosmos. This invisible anchor, the dark matter halo, is the true architect of our night sky. Think of it not as a solid sphere, but as a vast, diffuse cloud, a cosmic gravitational well whose pull is irresistible. Every galaxy we see is merely the visible heart of a much larger, unseen beast. Normal matter, the stuff of stars, planets, and us, is simply the luminous tracer, the glittering dust that settled at the bottom of these deep, dark wells. The halo's immense gravity acts as a cosmic construction site, first gathering the primordial hydrogen gas, and then compelling it to collapse and ignite into the first brilliant stars. The characteristics of this invisible foundation are everything. A massive, rapidly spinning halo might birth a majestic spiral galaxy like our own Milky Way, its arms tracing the whirlpool of dark matter's motion. A slower, more placid halo could lead to a featureless elliptical galaxy, a quiet stellar city. So when you look up at the band of the Milky Way, you are not just seeing stars. You are witnessing the visible signature of an immense, invisible presence, a dark matter halo whose gravitational embrace has held our galaxy together for billions of years. But how does this hidden skeleton organize itself into the larger structures of the cosmic web? These filaments are the universe's great rivers, flowing with the raw material of creation. Stretching across unimaginable distances for hundreds of millions of light years, they form a brilliant, interconnected network. This is where the cosmos truly comes to life. Within these dense threads, the primordial hydrogen and helium gas left over from the Big Bang is channeled and concentrated. This gas, heated to incredible temperatures, does not simply sit still. It flows along these cosmic superhighways, a continuous delivery system of fuel destined for hungry galaxies. When a galaxy is lucky enough to reside within one of these vibrant filaments, its fate is dramatically different. It is bathed in this constant influx of material, leading to explosive bursts of star formation. These galactic cities glow with the light of newborn stars, their properties shaped by the rich environment that surrounds them. They are the thriving metropolises of the cosmos, in stark contrast to the lonely, starved galaxies adrift in the empty voids. By tracing the path of these cosmic rivers, we are essentially mapping the flow of life itself, the very process that builds galaxies and fills the darkness with light. And this flowing material, this river of gas, is all guided toward specific, monumental destinations. Where these cosmic rivers of dark matter and gas intersect, they forge the universe's grandest metropolises. Galaxy clusters are the colossal cities of the cosmos, the largest structures held together by their own gravity. Within a single cluster, you can find not dozens, but hundreds or even thousands of individual galaxies, all swarming around a common center. This immense population is bathed in a seething ocean of superheated gas, and all of it is anchored by a staggering concentration of dark matter, a gravitational heart so powerful it warps the very space around it. The environment inside one of these clusters is incredibly intense and often violent. A galaxy entering this crowded urban center for the first time faces a dramatic transformation. The immense gravitational tides from the cluster and the pressure from the scorching intergalactic gas can efficiently strip away a galaxy's own reservoir of cold hydrogen. This gas is the very fuel for new stars, and without it, the galaxy's star-forming factories grind to a halt. What remains is a galaxy that is, for all intents and purposes, retired. Astronomers often call these red and dead galaxies. They're populations of stars aging collectively without any new, bright blue stars to renew them. This process is a key reason why the cores of these massive clusters are dominated by these quiet, elliptical galaxies. Yet, for all their transformative power, these clusters are far more than just endpoints. They are unparalleled natural laboratories, allowing us to witness physics under conditions we could never hope to recreate on Earth. By studying the violent collisions between entire clusters, we have gathered some of the most compelling evidence for the existence of dark matter itself. To truly appreciate the crowded majesty of these cosmic cities, however, we must also understand the profound emptiness that surrounds them. Yet for every brilliant galactic city, there exists its opposite, a realm of profound emptiness. These are the cosmic voids, the great deserts of the universe. They are not merely empty space between the bright structures, but fundamental components of the cosmic web itself, defining its shape through their sheer absence. If the filaments are the superhighways and the clusters are the metropolises, then the voids are the continent-spanning wilderness areas, occupying the overwhelming majority of the cosmos's volume. Within these vast regions, matter is exceptionally scarce. A single, lonely galaxy might find itself separated from its nearest neighbor by tens of millions of light-years of near-nothingness. This isolation has profound consequences. A galaxy born into a void is like a solitary tree in an open field, its growth shaped entirely by its own resources. Without the constant gravitational nudges and collisions that galaxies experience in crowded filaments, these void galaxies often develop into strange, irregular forms. They are frequently smaller, bluer, and more chaotic in their structure, as they have been left to evolve in quiet solitude for billions of years. Their star formation can be a slow, steady burn, as they are not subjected to the violent events that can quickly exhaust a galaxy's gas in a dense cluster. The very existence of these voids is just as critical to our understanding of the cosmos as the dazzling clusters. They are the negative space in the universe's grand painting, and by studying their size and distribution, cosmologists can perform a crucial test. The way these voids expand and evolve over time provides one of our clearest windows into the mysterious force of dark energy. This repulsive energy, which seems to be accelerating the expansion of the entire universe, acts most dramatically on these empty regions, stretching them even wider and making them even emptier. So, the great silence of the voids is not a passive emptiness, but an active, evolving feature. telling a story about the most dominant and least understood component of our universe. This stark contrast between the crowded and the empty, the bright and the dark, brings us face to face with the dynamic processes that continuously weave and reweave the entire cosmic tapestry. This profound emptiness provides one of our clearest views into the universe's greatest mystery. While the crowded clusters and filaments are locked in a constant gravitational struggle, the voids are different. With so little matter to hold them back, these vast regions of nothingness become uniquely sensitive to the influence of dark energy. This repulsive force, which seems to be an inherent property of space itself, finds its greatest freedom to act within these cosmic deserts. The effect is a kind of cosmic amplification. As the universe expands, the voids expand even faster, stretching and becoming emptier at a rate that outpaces the rest of the cosmic web. They are not static bubbles, but are actively being inflated by this mysterious energy. This is why scientists now see these voids as fundamental laboratories. By meticulously measuring how the shapes and sizes of these empty regions change over billions of years, we can take the pulse of dark energy itself. We can measure its strength and trace how its influence has changed across cosmic history. Each mapped void is like a single day, a point in a grand experiment, turning the great nothingness into a precise tool for understanding the cosmos's ultimate fate. The question of whether the universe will expand forever, tear itself apart, or eventually collapse, may well be answered by studying its emptiest places. But how did we even begin to perceive this invisible architecture, to map the unmappable on such an impossible scale? For centuries, our cosmic perspective was one of serene uniformity. Astronomers gazing into the heavens saw a universe where galaxies were scattered like isolated islands in a vast, smooth sea. This comforting view of a fundamentally homogeneous cosmos began to crumble as our tools grew sharper. The true turning point arrived not with a single telescope image, but with a profound shift in methodology, the birth of the Grand Galaxy Survey. By patiently cataloging the precise three-dimensional positions of not just hundreds, but millions of galaxies, a new picture began to emerge from the data. The galaxies were not randomly distributed. They were arranged in vast, intersecting walls and long, lonely chains, with tremendous empty spaces stretching between them. The theoretical predictions of a structured universe, built on the foundation of dark matter and primordial ripples, finally had their visual proof. Groundbreaking work by astronomers like J. Richard Gott III and Mario Jurek translated these millions of data points into breathtaking three-dimensional maps. For the first time, humanity could see the cosmic web not just as a concept, but as a tangible, sprawling architecture. The universe was not a simple, smooth soup. It was an immense and complex sponge. This historical shift from a homogeneous cosmos to a structured web is one of the most important in all of modern cosmology. It redefined our very place in the universe, showing that our Milky Way is part of a specific filament, a local group, a supercluster, all interconnected nodes in a grand design. This hard-won knowledge, born from decades of patient observation, set the stage for the next great leap, the tools that would allow us to move from simply mapping the web's glowing galaxies to perceiving its entire dark matter skeleton. Mapping the cosmic web requires a shift in perspective, from observing single points of light to comprehending the entire tapestry at once. This monumental task is the work of ambitious sky surveys, projects with names like the Sloan Digital Sky Survey and the Dark Energy Survey. Imagine a census of the cosmos, where powerful telescopes automatically scan vast swaths of the night sky, night after night, meticulously recording the positions and distances of millions of galaxies. This data does not remain as a simple list. It is transformed into a three-dimensional map of the local universe, a digital cosmos where every point of light has a known address in space. But how do you find the web's structure in a cloud of points? This is where sophisticated computer algorithms come into play, acting as our cosmic cartographers. They analyze the immense galaxy maps using techniques with evocative names like the skeleton method. This process is akin to looking at a map of all the towns and cities on Earth, and using their density to trace out the invisible lines of the interstate highway system that connects them. The algorithm identifies the dense lines of galaxies, the underlying spines of the filaments, and the vast, empty tracts of the voids. It connects the dots on a scale no human mind could, revealing the grand architecture hidden within the data. These resulting maps are more than just beautiful visualizations. They are our fundamental windows into the large-scale structure of the universe, providing the raw, observational data that rigorously tests our most advanced cosmological models. Every filament traced and every void measured is a point of verification for our theories of dark matter and dark energy. With this incredibly detailed data in hand, we possess a snapshot of the cosmic web's current state. This allows us to run the cosmic film in reverse, to simulate the entire universe from its earliest moments, watching as gravity sculpts a smooth, primordial soup into the intricate, web-like structure we observe today. These virtual universes, born from data and governed by the laws of physics, are the ultimate testing grounds for our understanding of everything. These digital universes are born from lines of code and the raw power of physics. To truly see the cosmic web form, scientists run the universe in reverse, using some of the most powerful supercomputers on Earth. Projects with names like Illustris TNG and the Millennium Run are not simple animations. They are exhaustive calculations that begin with the pristine conditions of the infant cosmos, just after the Big Bang. They take the faint primordial ripples we detect in the cosmic microwave background and set them in motion, applying the unyielding laws of gravity, gas dynamics, and dark matter physics. Over virtual billions of years, these simulations watch as gravity amplifies those tiny seeds. They witness the dark matter condense first into a vast, invisible skeleton. Then they see normal matter, the hydrogen and helium gas, flow into that gravitational scaffolding, cooling and collapsing to ignite the first stars and assemble the first galaxies. The result is nothing short of miraculous. These virtual universes, generated entirely by mathematical rules, reliably reproduce the very cosmic web we observe. They are filled with the same intricate filaments, the same massive galaxy clusters, and the same vast, empty voids that fill our own night sky. This is the ultimate validation that our underlying theories are on the right track. But these simulations are far more than just a cosmic mirror. They are dynamic laboratories where we can experiment with the universe itself. Researchers can tweak the fundamental rules, altering the properties of dark matter or the strength of various feedback processes. They can watch as supernova explosions or ravenous black holes at the hearts of galaxies blast energy back out into space, regulating star formation and shaping the galaxies we see today. By running these countless virtual experiments and meticulously comparing the results to the real data from sky surveys, we can isolate which physical recipes are correct. We can refine our understanding of the cosmos not just by observing it, but by actively recreating its entire history. This powerful feedback loop between digital creation and real-world observation is how we test the very laws that govern existence, allowing us to trace a direct line from the first quantum whisper to the grand cosmic tapestry we call home. The entire cosmic architecture we see today was imprinted upon the universe in its very first moments. In a fleeting, almost incomprehensible instant after the Big Bang, the cosmos underwent a violent growth spurt known as inflation, expanding faster than the speed of light. Within that furious expansion, the empty vacuum of space itself was not perfectly smooth. It was a seething quantum foam, bubbling with tiny, spontaneous fluctuations. Energy would flicker into existence and then vanish, a temporary loan from the laws of physics. As the universe inflated at a staggering rate, these subatomic ripples were stretched to proportions beyond human comprehension. What began as a quantum whisper smaller than a single proton was magnified to span thousands of light years. These stretched imperfections became the faintest variations in density, tiny hills and valleys in the very fabric of spacetime. They were the universe's original instructions, a cosmic blueprint written in a code of density. For hundreds of millions of years, the universe remained a dark, featureless sea of hot gas. But those tiny density differences were destiny. A region with just a little more mass had a slightly stronger gravitational pull. Over cosmic time, that small advantage became self-reinforcing, slowly drawing in more and more of the surrounding hydrogen and dark matter. Gravity acted with infinite patience, amplifying these initial seeds, pulling matter from the valleys to pile up on the hills. The denser regions eventually collapsed under their own weight, forming the first stars and galaxies, while the less dense regions emptied out, becoming the great voids. This is the profound link between the smallest and largest scales of reality. The same quantum rules that govern particles in a laboratory created the slight unevenness that allowed galaxies, stars, and planets to form at all. Without those primordial seeds, the universe would have remained a perfectly smooth, dark, and forever empty ocean, with no islands of light to ever emerge. All of this structure was set in motion by gravity, the master sculptor waiting in the wings. Gravity is the patient artist of the cosmos, working on a timescale we can scarcely comprehend. Its guiding principle is deceptively simple, an unrelenting pull that never switches off. Over billions of years, this gentle but persistent force took the faint primordial blueprint and began to carve. Wherever there was a slight overdensity, a tiny hill in the fabric of the early universe, gravity's influence was just a little bit stronger. It began to pull, attracting wisps of dark matter and specks of primordial gas from the surrounding areas. This was the birth of the very first proto-filaments, the faintest threads in what would become a cosmic tapestry. This process is a powerful feedback loop, a snowball effect on a universal scale. As a region gains a little more mass, its gravitational pull increases. That stronger pull then draws in even more matter from a wider area, making the region denser still and further amplifying its gravity. It is a cycle of cosmic growth that feeds upon itself. What began as a microscopic imperfection steadily gathers an entire universe of material. This is the mechanism of gravitational instability, the engine that transformed a nearly smooth cosmos into the complex, hierarchical structure we see. But here lies a profound puzzle, one that reshaped our understanding of gravity's role. For this entire sculpting process to work on the scale we observe, for the great walls and clusters to form in the time available since the Big Bang, there simply was not enough normal matter. The glittering galaxies we see are not enough to account for the immense gravitational wells that had to form. Gravity, it turns out, was not working with the material we could see. It had a silent partner, an invisible workforce that provided the overwhelming majority of the mass. This is the enduring mystery of dark matter. Gravity's patient work left behind more than just a cosmic skeleton. It left a whisper of its first movements. Embedded deep within the grand design of the cosmic web is a ghostly echo, a fossilized imprint from the universe's earliest, most violent days. This echo is known as the Baryonic acoustic oscillation. To understand it, you have to travel back to a time before atoms, when the entire cosmos was a seething, opaque soup of particles and intense light. In this primordial plasma, gravity was trying to pull matter inward, while the tremendous pressure of the light was pushing it outward. This created a titanic struggle, generating powerful sound waves that rippled through the fiery fluid at over half the speed of light. Then, in a single, transformative moment, the universe cooled enough for atoms to form. The light, suddenly freed, streamed away in every direction, and the pressure that had been driving those sound waves simply vanished. The waves froze in place instantly, leaving a permanent, spherical shell of matter around every initial overdensity. Think of it like a cosmic raindrop hitting the surface of a pond, creating a ripple that expands outward until the pond suddenly and completely freezes solid, preserving the ripple forever. The scale of that frozen ripple is staggering. A standard ruler etched into the fabric of space, measuring about 500 million light-years across. Today, billions of years later, we can still detect its signature. When astronomers map millions of galaxies, they find a subtle but statistically undeniable preference. There are slightly more pairs of galaxies separated by this exact cosmic distance than by any other. It is as if the universe has a faint, recurring pattern woven into its tapestry, a pattern set when it was just an infant. This makes the oscillation a gift from the early universe, a perfect standard ruler. Because we know its original size with great precision, we can measure how it appears stretched or compressed in our sky at different distances, and thus at different eras of cosmic history. This allows us to track the expansion rate of the universe over billions of years with phenomenal accuracy, turning the cosmic web itself into a direct probe for the mysterious force of dark energy. This fossilized sound wave connects the first frantic moments of creation directly to the majestic, evolving structure we see today, a structure that is never truly at rest. The cosmic web is a dynamic arena, and its crowded superhighways are often the stage for spectacular galactic collisions. Within the dense filaments and clusters, galaxies are constantly pulled into intricate gravitational dances. When two galaxies swing past each other in a close encounter, their mutual gravity creates immense tidal forces. These forces violently stir up the vast reservoirs of cold gas within them, compressing the gas and triggering firestorms of new star birth. The galaxies themselves can be stretched and warped, their stars pulled out into long, shimmering streams known as tidal tails, beautiful scars from a gravitational embrace. Sometimes this dance does not end with a mere pass. If the galaxies lose enough momentum, their fate is sealed. They will slowly spiral inward over hundreds of millions of years, eventually merging into a single new galaxy. This is a primary way galaxies grow and evolve. A large spiral galaxy like our Milky Way is likely the product of numerous such mergers in its deep past, built from the consumption of smaller galactic companions. This relentless process is written into our own future. The Milky Way and the Andromeda Galaxy are currently hurtling toward one another, pulled together by the collective gravity of our local filamentary structure. In about 4 billion years, these two great spirals will begin a billion-year-long merger, their stars flung into new orbits, their gas colliding to ignite a final, brilliant burst of star formation. The result will be a new, larger galaxy, likely a featureless elliptical, a quiet retirement after a violent union. These interactions show that the cosmic web is more than a map of locations. It is a living system that dictates not just where a galaxy resides, but the entire story of its life, from its birth in primordial gas to its ultimate transformation through collision. The violent collisions and galactic dances we observe are not the only forces shaping the cosmic narrative. Scattered between the brilliant galaxies, woven through the very filaments of the cosmic web, lies a hidden ocean of matter. This is the warm, hot intergalactic medium, a name that perfectly captures its elusive nature. It is a diffuse, superheated gas, reaching temperatures of millions of degrees, and it represents the single largest reservoir of ordinary matter in the entire universe. For decades, cosmologists faced a puzzling mystery. Their most trusted theories provided a precise accounting of how much normal matter, the protons and neutrons that make up stars, planets, and us, should have been created in the Big Bang. Yet, when they added up all the visible matter in every galaxy and cluster, the numbers fell dramatically short. A huge portion of the universe's ordinary stuff was simply missing. The answer, it turns out, was not in the bright islands of light, but in the dark seas between them. The whim is that missing matter. It is the ghost in the machine, the invisible ink that completes the cosmic ledger. But how do you observe a gas that is so hot and thin it barely glows? Its incredible temperature means it does not emit the kind of light our telescopes are built to see easily. Instead, astronomers must become cosmic detectives, using indirect methods to find its signature. They train their most powerful observatories on the brightest beacons in the universe, quasars. As the intense light from a distant quasar travels across billions of light-years to reach us, it passes through these vast, hot filaments. The whim does not block the light, but it does steal a little bit of it, imprinting specific, telltale absorption lines onto the quasar's spectrum. It is like analyzing a brilliant spotlight after it has passed through a specific, nearly invisible fog. By identifying the unique chemical fingerprints left in the light, scientists can confirm the presence of this incredibly diffuse gas and even measure its temperature and composition. This discovery finally closes the case on the missing baryon problem, confirming that the majority of normal matter exists not in stars, but in this vast intergalactic reservoir. This hidden ocean is not a static pool. It is part of a grand cosmic recycling system. Galaxies themselves contribute to it through colossal events. When massive stars explode as supernova, or when material is ejected from supermassive black holes, they drive powerful winds that blast gas right out of the galaxy and into the surrounding filaments. This enriched material then becomes part of the whim, where it may eventually cool and fall back onto another galaxy, fueling a new generation of stars in a cycle that has continued for billions of years. The cosmic web is far more than a map of galaxies. It is a dynamic, breathing ecosystem with rivers of hidden, superheated gas flowing through its veins, continually shaping the destiny of every luminous island it connects. These brilliant galactic engines do more than just illuminate the darkness. They actively reshape the world around them. A galaxy is not a silent island, but a roaring factory whose operations send powerful shockwaves through its own neighborhood. This is the crucial concept of galactic feedback, a self-regulating cycle where the life and death of stars dictates the future of the galaxy itself. When the most massive stars reach the end of their brief, brilliant lives, they do not fade quietly. They explode as supernova, detonating with the force of a billion suns. These colossal blasts do two things simultaneously. They flood the surrounding space with powerful shockwaves that heat the cold, star-forming gas to incredible temperatures, preventing it from immediately collapsing into new stars. And they drive ferocious winds, hurricanes of energy that can blow the galaxy's very building blocks, its reservoirs of hydrogen gas, clear out into intergalactic space. This process acts as a cosmic thermostat. If star formation becomes too rampant, too many supernovae will quickly heat or expel the remaining gas, putting a brake on the creation of the next stellar generation. It is a cycle of boom and bust that prevents galaxies from burning through their fuel too quickly, ensuring a long, sustainable life. But there is another, even more powerful regulator at work, hidden in the very heart of the galaxy. Lurking at the center of nearly every large galaxy, including our own Milky Way, is a supermassive black hole. For most of the time, these cosmic monsters are quiet, dormant giants. But when a steady stream of gas and stars spirals into their gravitational clutches, the black hole awakens, transforming into an active galactic nucleus. The infalling material does not cross the event horizon silently. It swirls into an intensely hot, bright disk of matter, and as it plummets inward, it can trigger the launch of jets and winds of unbelievable power. These outflows, channeled by immense magnetic fields, can blast across the galaxy for tens of thousands of light years. The energy released by a single, feeding supermassive black hole can outshine its entire host galaxy for millions of years. This incredible outpouring of energy violently heats the surrounding gas, effectively shutting down the galaxy's ability to form new stars by starving its stellar nurseries of cold fuel. It is the ultimate form of feedback, a celestial governor that keeps galactic growth in check. Without this regulation, galaxies would likely grow to monstrous, unstable sizes, consuming all their gas in a single, brief burst of star formation. The entire cosmic ecosystem would look profoundly different. This constant push and pull between creation and destruction does more than just regulate a galaxy's size. It seeds the entire cosmic web with the very elements necessary for planets and life. Those supernova explosions and black hole winds are cosmic alchemists. Within the hearts of stars and in the fury of their deaths, simple hydrogen and helium are forged into heavier elements, carbon, oxygen, iron, all the way up to gold and uranium. The feedback processes then act as a delivery system, blasting these newly forged elements out of the galaxy and into the vast filaments of the warm, hot intergalactic medium. This enriches the entire cosmic ecosystem, polluting the pristine gas with the building blocks of rocky worlds and, ultimately, living organisms. The iron in your blood and the calcium in your bones were created in a long-dead star, and then scattered across the cosmos by one of these violent feedback events billions of years ago. This reveals a profound truth about our place in the cosmic web. The relationship between a galaxy and its environment is not a one-way street. The cosmic web dictates where a galaxy forms, but the galaxy, through its own intense life cycle, then gives back, regulating its growth and enriching the space around it for generations to come. This intricate, co-evolutionary dance is what creates the stunning diversity of galaxies we see. From quiet red ellipticals to vibrant blue spirals, each one a unique testament to the balance between the forces of construction and the forces of regulation. Your cosmic address determines the very shape of your galaxy. This is the profound truth revealed by the morphology density relation, a cornerstone of modern astronomy. Where a galaxy lives within the vast cosmic web directly dictates its physical form and its future. In the dense, urban cores of galaxy clusters, the dominant residents are smooth, featureless elliptical galaxies. These are the quiet retirement communities of the cosmos, where star formation has long since ceased, leaving behind a population of aging, red stars. Their peaceful appearance, however, belies a violent past. The intense environment of a cluster is a galactic battlefield. Galaxies moving at incredible speeds experience constant gravitational harassment from their countless neighbors. More critically, they plunge through a seething ocean of superheated gas that fills the cluster. This intergalactic plasma acts like a powerful cosmic wind, efficiently stripping away a galaxy's cold hydrogen gas, the very raw material needed to create new stars. A spiral galaxy entering this environment has its star-forming fuel ripped away, its spiral arms fading as it is transformed or quenched into a passive elliptical. This is a one-way street, a fundamental change in a galaxy's destiny dictated entirely by its location. In stark contrast, the quieter suburbs of the universe tell a different story. Within the sprawling filaments and the isolated field environments, spiral galaxies thrive. These are the vibrant stellar nurseries, their graceful arms alive with the blue glow of young, massive stars. Here, galaxies are spared the relentless violence of the cluster core. They can hold onto their precious gas reservoirs, allowing for sustained and peaceful star formation over billions of years. This clear environmental divide is one of the most direct pieces of evidence we have that a galaxy is not an island. Its entire life story, from its birth to its eventual retirement, is written by the invisible hand of the cosmic web. The grand architecture of the universe does not just place the galaxies, it sculpts them. This primordial echo, the cosmic microwave background, is more than a distant relic. It has become a powerful scientific tool, a flashlight we shine into the cosmic darkness to reveal what ordinary light cannot. One of its most brilliant applications is a phenomenon known as the Sunyaev-Zeldovich effect. Imagine the ancient light from the Big Bang, traveling for nearly 14 billion years on a perfectly straight path to reach our telescopes. But on its long journey, some of these photons pass through the immense, superheated gas that fills a massive galaxy cluster. This gas is so incredibly hot that its electrons are moving at a significant fraction of the speed of light. When a low-energy cosmic microwave background photon encounters one of these frenetic electrons, something remarkable happens. The photon gets a tiny kick, a boost of energy, like a ping-pong ball being struck by a swinging tennis racket. This subtle interaction leaves a specific, telltale fingerprint on the background radiation. In the precise frequencies where the CMB should appear coldest, the cluster's region now appears slightly warmer. It is a minuscule distortion, a shadow that is actually a brighter spot in a specific light. For astronomers, this is a gift. The strength of this distortion depends only on the density and temperature of the hot cluster gas, not on how far away the cluster is. This means we can use this effect to find galaxy clusters at staggering distances, one so remote their light is too faint for optical telescopes to easily spot. By scanning the sky for these specific distortions in the cosmic microwave background, we can essentially take a census of the most massive nodes in the cosmic web across the entire observable universe. It is like using the oldest light in existence as a backlight, illuminating the silhouettes of the universe's grandest structures and revealing a hidden layer of the cosmic architecture. To perceive the fine threads of this cosmic tapestry, we must learn to read with a different kind of light. The most delicate filaments of the web, the wispy tendrils of hydrogen gas that trace the dark matter skeleton, are far too faint and diffuse to see directly. Their presence is revealed only when we use the universe's own natural flashlights, the brilliant beacons known as quasars. The light from a single, distant quasar embarks on an epic journey across billions of light years to reach our telescopes. Along its path, it does not travel through empty space. It slices through a labyrinth of these invisible hydrogen clouds, each one a tiny part of a vast cosmic filament. And every single cloud it passes through leaves a mark. The neutral hydrogen atoms within these clouds are tuned to absorb one very specific color of ultraviolet light, a wavelength known as Lyman-Alpha. As the quasar's light journeys toward us, each intervening cloud steals a little bit of this specific color. The result, when we finally capture the light and spread it out into a spectrum, is breathtaking. Instead of a smooth, clean rainbow of colors, we see a veritable forest of dark lines. Each line is a missing piece, a specific fingerprint left by a single cloud of hydrogen at a specific distance. This is the Lyman-Alpha Forest, a dense thicket of absorption lines that tells the story of everything the light encountered on its long path. By reading this forest line by line, astronomers can perform a kind of cosmic tomography. They can reconstruct the precise distribution of the gas, measuring its density and temperature across unimaginable distances. It is as if we are using the quasar's light to take an X-ray of the universe, revealing the intricate, wispy veins of the cosmic web that would otherwise remain completely hidden. This technique provides our most detailed map of the gaseous highways that feed galaxies, allowing us to study the cosmic web's finest threads and understand how raw material flows from the vast emptiness into the brilliant cities of stars. This new decade of discovery is set to rewrite our cosmic maps with instruments of staggering power. The Vera C. Rubin Observatory, perched atop a mountain in Chile, will undertake a monumental 10-year census of the sky known as the Legacy Survey of Space and Time. Its massive mirror and enormous digital camera will scan the heavens night after night, not just observing millions of galaxies, but watching them change. It will detect billions of galaxies, many so faint they are currently invisible to us, charting their positions with a precision that will reveal the cosmic web's fine structure in ways we have only dreamed of. But to truly understand the web, we need more than just positions. We need to know how far away each galaxy is, and that is where the space-based observatories take over. The Euclid Space Telescope and the upcoming Nancy Grace Roman Space Telescope are designed to see in the infrared, a type of light that cuts through cosmic dust. They will measure the subtle distortions in galaxy shapes caused by the gravitational lensing of dark matter, and crucially, they will pinpoint galaxy distances with phenomenal accuracy. Together, these ground and space-based giants will collaborate to construct the most detailed three-dimensional map of the universe ever attempted. This is not just a more detailed picture. It is a new kind of vision. With this map, scientists will be able to perform a cosmic dissection, tracing the evolution of the web's filaments and voids across billions of years. We will watch as the great voids expand under the influence of dark energy, testing whether its repulsive force has remained constant or changed over the lifetime of the cosmos. This unprecedented clarity might even reveal entirely new classes of structure, patterns in the distribution of galaxies that challenge our current theories. The hidden architecture of the universe is about to step into the light. Our most detailed maps of the cosmos still contain glaring blank spaces, regions where our theories falter and the universe refuses to conform. One of the most persistent of these puzzles is known as the missing satellites problem. Our most sophisticated simulations of cosmic evolution, which so beautifully recreate the grand filaments and clusters, tell a very specific story about our own Milky Way. They predict that our galaxy should be surrounded by a vast swarm of small, dark satellite galaxies, perhaps hundreds of them, held in its gravitational embrace. Yet when we look, we find only a few dozen. It is as if our cosmic census is missing an entire population. This discrepancy suggests a fundamental gap in our understanding, either in how small galaxies form or in the very nature of the dark matter that anchors them. Perhaps the smallest clumps of dark matter never manage to ignite stars and remain forever dark and invisible. Or perhaps the intense light from the first stars blasted away the gas from these tiny halos, preventing them from ever becoming the bright galaxies we could see. The silence of these missing satellites echoes through our models, a quiet but persistent reminder that our picture is incomplete. This puzzle of the unseen is matched by a mystery of immense power, the precise mechanics of galactic feedback. We know that stars and black holes act as cosmic regulators, but the exact physics of how they do this remains one of the field's great challenges. How exactly does the raw energy from a supernova explosion transfer its force to the cold gas clouds light years away? What are the intricate processes within a black hole's accretion disk that allow it to launch jets capable of heating an entire galaxy's worth of gas? We understand the story in broad strokes, but the fine print, the crucial details of this energy coupling, are still being decoded. It is the difference between knowing that a wind can extinguish a candle and understanding the precise turbulence of the air that snuffs out the flame. Without this deeper knowledge, we cannot fully predict how a galaxy will grow and change over time, leaving a crucial chapter of its life story unwritten. At the very foundation of all these mysteries lies the greatest unknown of all, the true identity of dark matter. For decades, the leading candidate has been a hypothetical, slow-moving particle known as a WIMP, a weakly interacting massive particle. This model has been spectacularly successful at explaining the large-scale architecture of the cosmic web, how the great filaments and clusters assembled over time. Yet, despite decades of searching with incredibly sensitive detectors buried deep underground, we have not directly captured a single one of these phantom particles. Their continued illusion forces us to consider other, even more exotic possibilities. Could dark matter be made of particles that interact with each other through a hidden force, a secret physics that only governs the invisible world? Or is it something entirely different, a flaw in our understanding of gravity itself that manifests only on the grandest scales? The answer will rewrite the rules of the cosmos. These unresolved questions are not failures of our science, but rather the guiding lights for its future. They are the tantalizing clues that assure us the cosmic web still holds profound secrets, its darkest strands waiting to reveal a deeper truth about the universe we call home. The universe's grand architecture may hold a secret recipe for life itself. This leads us to a profound speculative question. Could the very structure of the cosmic web, from its dense clusters to its empty voids, influence the potential for life to emerge on distant worlds? The environment a galaxy calls home might be just as critical as the galaxy itself. Consider the chaotic core of a massive galaxy cluster. This is a hostile realm for any fledgling planetary system. Close encounters between stars are a constant threat, their gravitational pull capable of hurling planets from their stable orbits into the cold depths of interstellar space. These crowded neighborhoods also bathe their inhabitants in intense radiation from countless stellar sources and active black holes, creating conditions that could sterilize entire worlds. A planet in such a place might struggle to maintain the stable, gentle conditions life seems to require. On the opposite end of the spectrum, a galaxy adrift in the profound solitude of a cosmic void faces a different kind of challenge. Its great isolation, a result of evolving in quiet emptiness, might mean it has experienced fewer of the galactic collisions and mergers that drive the cycles of star birth and death. These violent events are the universe's primary foundries, creating and scattering the heavy elements like carbon, oxygen, and iron, the very building blocks of rocky planets and living organisms. A void galaxy, having witnessed fewer generations of supernova, could be impoverished in these crucial elements, potentially lacking the raw material to form Earth-like worlds at all. This line of thinking suggests the concept of a habitable zone might extend far beyond a single star or galaxy. Perhaps there is a cosmic web habitable zone. The ideal location for life may not be in the crowded urban centers or the empty deserts, but in the cosmic suburbs, the outer regions of galaxy clusters or the quieter, more stable stretches of the great filaments. Here, a galaxy could enjoy the benefits of a richer environment, with ample heavy elements from past interactions, while being spared the relentless violence of the cluster core. It is a tantalizing possibility that connects the largest structures in existence to our own deepest questions about whether we are alone in the universe. This universal patterning, a fractal echo from the cosmic to the microscopic, is impossible to ignore. The same branching structure that defines the universe's grand design appears in the lightning bolt's path, the human lung's delicate airways, and the sprawling network of neurons inside your own brain. It is a pattern that nature returns to again and again, a fundamental blueprint for complexity and connection. This stunning visual resonance has drawn artists and scientists into a shared space of discovery, where data becomes a new kind of pigment. Cosmologists provide the raw numbers, the precise three-dimensional coordinates of millions of galaxies, and digital artists then translate this cosmic census into breathtaking visualizations. We are no longer just looking at graphs and charts. We are flying through a digital universe, watching filaments of light crystallize from a cloud of data points, making the invisible architecture of reality tangible for the first time. These collaborations extend beyond the screen into physical spaces. creating immersive art installations that allow you to step inside the cosmic web itself. Imagine walking through a room where suspended threads of light trace the universe's great walls, or standing beneath a dome where a simulation of the entire observable universe unfolds around you. These experiences are more than just beautiful, they are profound. They trigger a deep, intuitive recognition that the same laws of physics that govern the clustering of galaxies also influence the growth of a tree's roots searching for water or the formation of social networks linking human minds. This is where the line between empirical science and the search for beauty truly blurs. Our drive to map the cosmos is not so different from an artist's desire to capture a stunning landscape. Both are rooted in a fundamental human need to find patterns, to make connections, and to understand our place within a vast, interconnected whole. The cosmic web, in all its mathematical glory, reminds us that the universe is not just a place of physical laws, but a source of endless wonder and aesthetic inspiration. The precise laws governing our universe appear suspiciously fine-tuned for complexity. This line of reasoning leads to a profound and often debated idea known as the Anthropic Principle. In its simplest form, it suggests that the universe we are capable of observing must, by necessity, have properties that allow for observers to exist within it. This is not a claim of design, but rather a statement about the conditions required for our own presence. The cosmic web itself is a testament to this delicate balance. Consider the force of dark energy, the very engine driving the universe's accelerated expansion. Its observed strength is incredibly, almost impossibly, small. If the value of dark energy were just slightly larger, by a factor of perhaps 10, the consequences would have been catastrophic for structure. The repulsive force would have overwhelmed gravity's patient work in the universe's infancy, flinging matter apart before it could ever coalesce into the first proto-galaxies. The cosmic web would have been stillborn, resulting in a forever dark, smooth, and empty cosmos with no galaxies, no stars, no planets, and no one to wonder about its existence. The fact that we are here to map this grand architecture implies that we live in a universe where the dials were set to very specific values that permit the rich tapestry of structure we see. This startling realization forces us to confront two equally monumental possibilities. Either the fundamental constants of nature are the result of an unimaginably unlikely cosmic lottery win, a single, random roll of the dice that happened to produce a habitable universe, or our universe is just one among a vast multiverse. In a multiverse scenario, countless other universes may exist with different physical laws, most of them sterile and empty. We, of course, can only find ourselves in one of the rare, bio-friendly bubbles where the numbers align just right to build a cosmic web, and ultimately us. This principle turns our own existence into a fundamental piece of cosmological data, a clue that the story of the cosmos may be far wider and stranger than the single universe we call home. Our journey through this grand architecture reveals a universe of breathtaking interconnection. Every galaxy, from our own Milky Way to the most distant island of stars, is a single thread in this cosmic tapestry, its position and destiny shaped by forces operating on the largest scales imaginable. We have traced the invisible dark matter skeleton, navigated the flowing rivers of the filaments, and stood in the profound silence of the voids. We have witnessed how the gentlest whisper from the Big Bang was amplified by gravity's patient hand into the magnificent web we observe today. This is not a static monument but a living, breathing entity, a story still unfolding.